Welcome all. In this lab we are going to study about the FIR filter designing with window for band pass filter and band reject filter. Okay, in the previous lab we have studied about the low pass filter and high pass filter designing with window. Okay, so and in lab 8, 7 and 8 we have studied about the different kind of windows that we have for the FIR filter designing, and in lab 8 we have studied about the different kind of filter that we are designing of different kind of filter without window, right? So we are going to design the band pass and band reject filter with window in this lab, right? So for that let me start a new notebook. Okay, let me give the name as FIR with window okay. So I just change the name of the file, the notebook, and before proceeding to the content of today's class, let me list out the thing that we are going to discuss in this lab. Okay, like our previous lab, we are going to discuss the designing of FIR filter with different kind of windows that we have actually, and that 5 kind of window that we discussed in our previous lab, that we are going to that thing only we are going to implement in this lab. And in previous lab I show you the steps from SAR's lecture, from your theory classes, and I tell you what the changes that I have made here and how I implement that formula or the steps into my Python coding, right? In previous class we all go through that, right? So in today's lab we are going to discuss this thing. So I list out the things here in this cell: designing of FIR filter with window, right? So first one is, let me name it as serial number 3, because the first one is my low pass, then high pass, then I am naming that as the band pass, right? The band pass filter first band pass filter with different kind of windows that we have with, let me write, with panning first, Hamming then, okay, then we have Bartlett, then Blackman, then Kaiser, right? Then next is band reject filter or band stop filter, same thing, right? with this window. Okay, I have not mentioned window here. So with this window, right? So we are going to see individual filter with individual window function. Okay, so before starting, let me give you some basics about band pass filter and band reject filter. I think already you people already know, so still I am repeating the thing that for a band pass filter we have in that filter a range of frequency is passed through it, and other without means out of that range all frequency component will be blocked by that filter. Okay, so in band reject filter it's just opposite of that. What it will do is that we supply the band of suppose we give the cutoff frequency. In that cutoff all the frequency component which are present in between that cutoff frequency are blocked, right? Other than that cutoff frequency all the frequency component are passed by that filter, right? So I just repeat that thing. So let's start our coding. Okay, so we already did some basics on this window designing in our previous lab, so I am not going again into that picture that I have shown from SAR's lecture. I am directly moving to the coding part, right? So first I am going to import the libraries that I needed for today's class. So let me list out the thing first which we are going to need from NumPy. Import cos, sine, then pi, then absolute, arrange, then zeros, then log 10, right? From SciPy we don't need it. Okay, yeah, we need SciPy dot signal import Hamming. First Hamming, get it to be Hamming, then Hamming, then Bartlett, then Blackman, then Kaiser. Okay, and we have to import FIR win, then Fritz, right? Then next is from pylab import figure, then plot title, then x level, then y level, right? Then let x limit, maybe we need in the time of designing, so let's put that here so that we can use it, right? Okay, this much. If we need axis, then we will going to give the axis over here. So now I am not taking that. Okay, if any other module I want, then I will add it from this in this cell, right? So let me run it. Control shift, sorry, shift enter. Yeah, it's running actually. Let's wait. Yeah, it's completed. So now let's start our coding for the band pass filter first with Hanning window. So let me band pass filter with window. Okay, so let me make it as a heading. Okay, yeah. So first is designing of, or you may say band pass filter with Hanning window. Okay, so first for the user input, that is n, which is equal to eval input enter the order of the filter. Okay, then as it is a band pass filter, in our earlier classes we have seen that we have to supply a 2 cutoff frequency here, right? So for that I am supplying two variable fc1 comma fc2. Okay, is equal to eval input enter, sorry, the cutoff frequencies for band pass filter. Okay, so enter the cutoff frequencies for the band pass filter. Yeah. Then next we have to give another variable called fs. We are already familiar with this. That is for the sampling frequency, right? Enter the sampling frequency, enter the sampling frequency. Yes. Then the user input part is over. Okay, so you can give a heading over here that this is for the user input. Okay, then the next thing is that we are going to calculate the filter component using built-in function. In previous lab I told you about the built-in function and formula based filter coefficient, which are similar only. So here also we are going to check whether the values that are coming is equal or not, and you may say for our designing purpose this is very helpful, right? In the reason I have told in my previous class. So built-in formula built-in function or you may write like this using built-in function. Okay, so similar to the previous one, apps is equal to FIR win, then the order of the filter, that is capital N, comma, then we have to give here the cutoff frequency, normalized frequency, right? So for that what we have to do is fc1 divided by fs, comma, fc2 divided by fs, right? Then next is the pass time, pass 0 argument. Which is equal to band, right? Band pass. Okay, then here we have to supply the window type is equal to, here we are starting with Hanning, so I am giving Hanning. Okay, then yeah, this is I am not printing the coefficient, we already see in our previous lab that the filter coefficient that are generated from the built-in function, this command you may say is similar to that of the formula based filter coefficient, right? So I am not printing this filter coefficient here. I am just directly going to the window generation. Okay, window, or we may say Hanning window generation. Okay, for Hanning window generation, let me give a variable name as wn, which is equal to Hanning of what? Hanning of capital M, right? Yes. Then let me print the normalized frequency. Print normalized frequency, normalized cutoff frequencies, which is frequencies of band pass filter is that is fc1 divided by fs, next one is fc2 divided by fs, right? This will give us the normalized frequency. Then we want to find out the digital cutoff frequency. For finding that, let me give another variable name, that is omega c1, which is equal to, we already did that, fc1 divided by fs into, I have to make pi, right? Similarly, omega c2, which is equal to fc2 divided by fs into pi, right? Yes. So let me print this. Print digital cutoff frequency frequencies of band pass filter is omega c2, right? So these are my two digital frequency. Now the next step is to write down the formula based filter coefficient function, right? So using formula okay. So we are going to write the formula based approach for this. So as I told, we see that we have to declare a variable called alpha here, which is nothing but the order minus 1, this must be capital N, right? Order minus 1 divided by 2, right? Then we have generate two empty array HD, which is equal to zeros of length of capital N, and h, sorry, small h is equal to zeros of capital N, right? It will generate two empty array. After that we apply a for loop for small n in range of capital N colon if my small n is equal to alpha, then HD of n will be is equal to omega c2, this is the higher side, minus omega c1 divided by pi, right? Okay, so if we integrate that for a band pass filter, that function that we have studied in theory class, you will get these things. Okay, so you have to do this as a homework, and maybe you people have done in your theory copies, so please go through that. If you people didn't do it, so please do the integration for a band pass filter or band reject filter. In that you will get these things when the n is equal to alpha. This thing I have already make you understand in the previous lab, so I'm not going into deep into that. If people make integration, then you will get these things. Okay, so I'm going to the else part here. Else what we will get is that HD of, here I make a mistake, that n must be in square bracket, right? Yes, so SD of n is equal to psi omega c2 into n minus alpha. Okay, here must be some into side here. Alpha minus sine of omega c1 into n minus alpha. Okay, into n minus alpha, right? Then divided by, this will be divided by the whole thing, that is pi into n minus alpha. Okay, so this function you will get in the previous lab. We got what, that sine omega c into n minus alpha divided by pi into n minus alpha, right? In that integration we get that thing, but here the two frequency component is there. For that we will get, if we integrate that function that we saw in our theory classes, that steps that sir has taught us. So in that if we do that, then we will get the integration values as this. Okay, so we implement the formula. Now let's do the final step, that is the multiplication of the values, that is h of n is equal to hd of n into the window function wn of n, right? Okay, then we have to print, to just come out of the loop, because you can see the indentation here, and we just come out of the loop. I am giving the FIR band pass filter, or you may write, it will be better, band pass filter coefficient from the formula is coefficients from the formulas are will show the filter coefficient from the formula, right? Then okay, let me run it first, then we will go for the plotting and the frequency response analysis. Okay, so some error is there. Okay, can check. So mirror is good. Small omega c where I have written omega t. Yeah, here it is. Okay, it's a big code, so that's why I split into and split this and just find out the output. Then let me give 500 1000 bracket close, then sampling frequency h 2000. Oh sorry, I didn't provide the values here. H. Okay. So yeah, it's showing the filter coefficient, right? So now we can go for the frequency response analysis of this filter. So for that, okay, so for that we have to use the fix and let me frequency response analysis. Okay, so for that we have is equal to fix of taps comma WRN is equal to 1024, right? Then next step is dB is equal to 20 log 10 absolute of H, right? So the frequency response part is over now. Now we have to plot the frequency response of the filter. Plotting, right? So first plot is versus W divided by max of W comma absolute of H is with the line width of 3. Okay, line width Then put the title as it is a frequency response of band pass filter with Henning window with a font size okay. Now the X level normalized frequency okay. Then Y level is gain, okay. Then grid I have to make it as figure 1. Then figure 2 plot max of W into FS, comma then the title is frequency response of the band pass filter with Henning window font size of is equal to 50. Then X level is sorry, frequency in hertz. Put it in a bracket. Okay, then y level is gain in dB, right? Okay, I think it's over. Now put the grid. Then so okay, so it's a big program actually. Let's check whether we have okay, there must not be any mistake over here. So let me run the code. Yes, so it's 51. Then I'm giving as usual my cutoff frequencies, that is 500, 1000, bracket close. Then the sampling frequency as 2000, right? So now let's see what my outputs are. So these are my normalized frequency 0.25 and 0.5, right? And digital cutoff frequencies of the band pass filter is, these are my digital cutoff frequency, right? And these are my filter coefficient. Okay, so I have some error here, so let me, okay, I didn't call the grid here. From this, then let me run it again. Okay, $500, 1000, then the sampling frequency I am giving as 2000. Okay, still, oh, that will come so also. Oh, I forgot actually. Again have to make them. Okay, so I'm just running it again. Please add these those command over there, okay, from initial, otherwise you will go also get some kind of error. Sorry, 500, 1000. Okay, then this is as 2000. Yes, this is the frequency response of the filter, right? This is in the normalized frequency and this is in the hertz. To get a clear picture, we just did this, right? Okay, so this is about the, you can do one thing, you can check the filter, order of the filter, and try to visualize the thing again. Okay, I am giving here the order of the filter as 31, right? So check for the sake of understanding and changing the number, right? See, the slope is, how much is the slope here in normalized frequency. In hertz we are not going to notice this because uh, of this component over here, but in normalized frequency it is pretty much visible. The slope is very high over here, as I discussed these things in lab number 8. The slope is, as the order of the filter is decreasing, the slope will increase, right? So that thing happen over here. Okay, so this is all about the band pass filter with Hanning. So now let's see for the program for designing a band pass filter using Hamming window. So for that, let me give the heading that band pass filter with Hamming, right? Hamming window. Okay, so most of the coding that we have done for the Hamming is similar to, it's pretty much similar. That's why I am copying the thing over here. Okay, so okay, so let me paste it here. Then we will see one by one. Okay, what's the code is. We already seen this in the previous cell, the band pass with Hanning window. So I'm not going to explain the thing again. So let me make the changes that I have to do with for the designing of band pass filter with Hamming window. So first one is, I have to change this to Hamming, right? So my window gets changed to Hamming type now. Now I can proceed for proceed to the next thing. Other are the Hanning must be changed to Hamming. Okay, so this formula is same only, so we don't have to change anything here. Frequency response formula also same. So the changes that I have to make here is, I have to make this as Hamming. Okay, then this also change to as Hamming. Okay, so this is this much I think. So let me check it once again whether we need any other changes or not. So yeah, okay, we don't need anything else. So let me run this code, shift enter. So let me give the filter length as usual 51. Then I am providing the array of cutoff frequency similar to that of the previous one, that is 500 and 1000. Okay, enter. Then sampling frequency as 2000, right? So now we can check the frequency response of the filter. Okay, can check out the frequency response here. Okay, the normalized frequency are given here and the digital cutoff frequency is this one. Okay, and these are the filter coefficients. Okay, then this is the frequency response of the band pass filter with Hamming window, which are in the normalized frequency. We plot this graph in the normalized frequency range. Then the next one is the frequency response of band pass filter with Hamming window. In this we plot this in plot the frequency in hertz. Okay, so this is it. So now let's see for the our next window, that is with Bartlett window, right? So for that, let me I already copied the thing, so I have to make few changes. That is band pass filter with Bartlett window, right? So let me list that, and I have to make the requisite change here. So it's going to be changed as Bartlett, right? We have to change the window type as Bartlett. Okay, then yeah, I forgot to change here. Maybe yeah, it's must be as Hanning. It must be Hamming, right? Okay, let me run it again. Okay, I make a mistake over there. So, then okay, so some error is coming. So let me run it again. Yeah, right. So I make the changes over here, right? So the filter parameter is also changed here, so you can go through that because I didn't change the Hamming window generation here. Now it is okay. Okay, so now let's see with the Bartlett window what are the change that I have to make. I have to make this as Bartlett first. Okay, then make this as Bartlett, right? Then window is generated. Then other thing I have to change here is this Bartlett, right? Okay, then next here also make the change. So let me run it because I have changed all the thing. I think check it once because I already made a mistake in the previous program, so it will better to check it once again. Okay, everything is fine, so we can proceed now for running it. So control shift enter, then put the frequency 51, then and pass same as 500 and other one is 1000, right? Then sampling frequency is 2000, right? Okay, so you can see this is the frequency response that I have get in for the band pass filter using Bartlett window. Okay, so now let's see with Blackman window. Okay, so band pass filter with blackman window. Okay, so let me paste it here. Okay, so we can make the changes that we have to make this as blackman first, right? Then make this as blackman because we are designing with blackman window. Okay, then make this as also blackman. Okay, okay, now we'll do the next line. Here make the change that here it should be blackman, right? Then here also make it as a blackman. Okay, so everything is fine. Let's run it. T1, then 500 is the lower cutoff and the upper cutoff is 1000. Then 2000 is my sampling frequency, right? Okay, some error is coming here. Unknown window type. Yeah, must be it is small. Yeah, single N. That's why it is showing this. I thought it is double N. Okay, so see, now let's check. Then we'll make the change that we have to do. So 500 is lower, then 1000 is upper, then 2000 is my sampling frequency, right? Yeah, that's the actually thing that I have to. So this is the filter coefficients, right? You can check with the inbuilt and the formula uh, based filter coefficients, so it's up to you. I'm not checking every time. In the first program I have already checked the filter coefficients with both the type. Okay, so it's similar only, right? As I uh, show you in that type, right? So let me make the change that is similar, right? Yeah, okay, so this is the program for band pass filter with blackman window. I'm not running it, otherwise let me run it. It will be better. It will be changed and it will be there in my code. So next one is 2000, right? Yeah, so this is all about this frequency response of band pass with blackman window. Now let's see for the Kaiser window. Okay, as we know, for Kaiser window we have to make a not one to or two changes in the coding, but we have to make few more changes, like we have to add some values of beta over there. Okay, so what I did is I have write the code in the next cell, and I will tell you what I did actually in the coding one by one. so we can you will get a clear picture about the coding, right? So for that, let me show you the cell that I have already uh, write it. Okay, so first, this user input you people already know. So in that thing I have only added a variable called beta. Okay, in previous lab also we have seen, right? For Kaiser window we need a other parameter like not like, it's beta only, right? So in theory classes also we studied about this, the values of beta, right? So I just add a variable there that is beta, which is I am giving as 14, right? For Kaiser window beta is 14. So not 14, in 14 it will give a good result, right? In window types I already told about these things, the how to get other type of windows from Kaiser by giving a proper value to the beta, right? So I'm not going into that again. So next thing in the coding is user built-in form function, right? We did this one, tabs, to find out the tabs, and in window type we have to give as Kaiser, and we have to give another parameter that is beta. Okay, if we are designing a Kaiser window, then we have to give another parameter that is as beta. Okay, so next one is the window generation. In window generation, same thing I have did that, Kaiser, then number of length of the capital N is the order of the filter, right? So I have given order of the filter there, then the beta value I have given there 14. Okay, then I have did the same thing that I have done in the previous code. These are the few changes that you have to look into. Okay, so other thing is same only, because the formula is not going to change, right? Because the basic thing that we have studied in designing a FIR filter with window is same only, nothing to change. We have to only multiply the window type in that. So I have generated the Kaiser window and just multiply that to get the thing. Then I have find out the frequency response. Okay, so this is the thing. Now let me run this. Okay, so I am giving order of the filter as 51, then the lower cutoff is 500, right? Then the upper cutoff is 1000. Let me give the sampling frequency as 2000 as usual. So now press enter to see the output that we actually need, right? Okay, yeah, its figure is a little bit different, right? What's the make? Yeah, I add a figure size over here. So you people can add this in figure size in every program such that you will get a good picture, right? So this is the frequency response. Okay, so this is about the band pass filter with window, right? So let's see for the code to design a band stop, or you may say band reject filter. Okay, so band stop filter window, right? So we are going to see with each type of window how to design a bent stuff filter. Okay, we see for the bend pass filter. Now let's see for the bend stop filter. So what I'm going to do here is, let me first write a code for a single window. Okay, if time permits me, then I will go for the other windows, right? Yeah, okay. So let me write it very first, so such that we can cover more windows. If it will not happen, so if people just do that, it is pretty similar only. Okay, so let me first do with Bartlett window. I am choosing Bartlett. Okay, you, it will be better because Henning I already started from many times. So let me start with Bartlett. Bend stop filter with Bartlett window. Okay, so first is the user input, right? Similar to that of the previous code. So total n is equal to eval input as the order of the filter. Enter the of the, okay. Then next is our cutoff frequencies, right? So fc1 comma fc2 is equal to eval user input okay. So we have to enter the cutoff frequencies for, sorry, cutoff for band stop filter, BSF, right? Or you may call band reject filter also. Next is sampling frequency, capital FS. So eval input enter the sampling frequency. Okay, so this is about the user input. Now let's go to our next section, that is uh, getting the window with built-in function, right? So for that, let me give the comment that using window using built-in function. Okay, So we already seen. So tabs, we declare a variable tabs, then fill in comma, then we have to give, sorry, the cutoff frequencies C1 divided by Fs, comma, not small f, it is cap, then Fc2 divided by Fs, right? Then the next parameter for this is the pass zeros, where we have to specify, sorry, not zeros, it is 0 is equal to, I am taking as band stop. Okay, then the window type I am taking as uh, as I've already mentioned earlier, partlet. Okay, this is it. Then now for Bartlett window, okay, so for that we give a variable n which is equal to next print the normalized cutoff frequencies of band stop filter is then fc2 divided, divided by fs. Okay, then the next is c1, this is equal to bracket f c1, it's not c1 divided by fs into pi, right? Then similar to that, fc2 is equal to fc2 divided by fs into pi. Okay, so next let print this of band stop filter, sorry, is omega c1 comma omega c2. Okay, right, then we have to implement the formula that I have shown in the previous uh, programs. Also in lab 9 we have seen the formula that has been shared by sir with us, that figure that uh, steps. Okay, so we already seen that we have to only implement that, so it's same only formula, it's not going to change, right? So for that, what I will do here is, let me copy the formula part from here. Okay, it's same only, no changes. Okay, so I can copy all the things over here because it's pretty same. The changes that I have made, I have to make is I already made that. So let me copy the thing and paste such that we can save some time over here, right? Okay, so yeah, here we don't have to change anything, here also no. Here I have to make few changes, that is it's a band stop filter, right? It's band stop filter here also. Okay, its window type is Bartlett. Okay, here also change this window type as Bartlett. Okay, so I think it is clear. Okay, so this is it. Now let's check once again, because yeah, maybe. So, okay, here it is band stop. Okay, then Bartlett window generation. Yes. Then formula is same only, so we don't have, I'm not going into again to that implementation part, right? Then the frequency response I have used, it's similar, we already used these things in various coding. So now let's run this code and give the order of the filter. Now let's take it as 31. Okay, then put the cutoff 500 comma 1000, means in this range the filter is not going to allow any frequency component to pass through it, right? So let's see whether it is working or not. Give the sampling frequency as 2000. Okay,
So yeah, the sampling frequency is 2000. The normalized frequency we have got this and this. Then digital cutoff frequencies are these. Okay, you can see here that the the frequency component that are present in between 500 and thousands are not passed through it, right? Now let's check if we increase the order of the filter, how the frequency response is changing. Okay, so let's check, take it as 51, then take this as 500 and 1000, right? Then the sampling frequency put as usual 2000. Now let's see, we can check it here. Okay, so very less ripple is present in the stop band, right? So now let's, this is for the band stop filter. I start here with Bartlett. Now let's see with a other type of window. Now let's see with Hanning window first, then we go for Hamming. Okay, so for that, let me copy the things. Okay, so this is the band stop filter. I'm going to do it now. Hanning window. Okay, then the user input is same only, not, I'm not going to change that. Now let's change the window type as Hanning. Okay, then this has to be changed also, make it as Hanning. Okay, then the user formula is same, no changes we have to make over there. Next changes that we have to make here is this one with Hanning, right? Next is this one with Hanning. Okay, now it is well and good. We can now proceed for the let's for the its execution, right? So let's run it. I am giving the filter order of the filter as 51, next as first cutoff as 500, and my second cutoff as 1000. Okay, and the sampling frequency is 2000. Center to see whether we are getting. Okay, these are the coefficients. Here we have seen some ripple that are present in the stop band, right? So we in case of Bartlett we didn't have seen any kind of ripple in that stop band, right? But here there are some ripple. Okay, so this is with Hanning window. Now let's check with if the order of the filter is reducing, what kind of output that I am going to get from there. Okay, so here I am giving that order of the filter is 31 and my cutoff frequency is as usual 500 at 1000 and the sampling frequency is 2000. So now let's see what's the the slope is little very high, that's why it is. Okay, so in this way we can design the band stop filter with Hanning window. So now let's see for the Hamming window. Okay, band stop filter with Hamming window. Okay, so as I previously copied, so let me paste that, and now we will change the required changes that we have to made here in the code, right? The first one is we don't need this one first of all. Okay, then make this window type as Hamming. Okay, then make this as Hamming. Then we have to make the change here also. It's to be changed as Hamming, right? So next changes is here we don't need any changes. We have to make the change here, that is it is a Hamming window. Okay, then here also make it as a Hamming type. Okay, so now check it once again. Yeah, Hamming, we make the change there. Then here also Hamming. So let's run this code. Give first 51 first, then we will see for other frequencies. Okay, so we enter the cutoff frequencies as 500 and 1000, the upper cutoff and the lower cutoff and the upper cutoff. In that frequency band, no frequency will pass through, no frequency component will pass through the filter, right? Then we give the sampling frequency and press enter to see the filter coefficients and the frequency response of the filter, right? This is the frequency response of the filter, that is event stop filter. We didn't change here. Okay, other also I have to make change then. Where, yeah, I forgot to make changes about that. Here band pass is written, so be careful. That's the thing, that's why I am not copy pasting, and because you will make, if you make a single, yeah, from starting onwards I make the wrong thing, right? So please don't copy paste, try to write, as it is the same code. I know uh, here I am copying because I want to save some time, because of the time constraint I just copied the thing and pasting it. So please people, if you are copying and pasting also, please be careful with the changes that I am making over here, right? Such that it will not hamper your result. So I'm not running it. If I run, then it will take more time also. So I make the change here. So let me run the last code with Hamming. Okay, T1, then the cutoff frequencies as 500 and 1000, right? Then the sampling frequency as 2000. Okay, so now it is, got it. So this is for the band stop filter using Hamming window. Now we left with two type of window, that is Blackman window and Kaiser window, right? So now let's do for the Blackman window, and in the next and our last coding we will see the band stop filter for the with Kaiser window, right? So let me write the code for the Blackman window with Blackman window. Okay, so sorry for the noises. Okay, so outside noises are not available here. Okay, so what I will do here is, let me paste the code that I have already copied from the previous coding. Then now let's make the changes from the beginning, otherwise we'll make some error. Yes, so now we have to make this window type as a Blackman, right? Blackman, then make this as also Blackman. Okay, with this also as Blackman, right? Okay, so other thing, right, in the below in the plotting section we have to make few changes. Here the window type has to change as Blackman window. Okay, so next here also we have to make this is a band stop filter, so BSF. Okay, band stop filter or band reject filter, sometimes we called it as a band reject filter also. Black pen window, right? I think it is clear and out, so we can run it. So now let's run it. Shift enter, give as 51. Then the cutoff I am going to give here is similar. I am keeping the cutoff frequency similar and that sampling frequency is similar to give you a clear result that if I use different cutoff and different sampling frequency, suppose I am using that, so you people get confused over there, right? Because you will not get a clear comparison of that. If you are comparing the values of our parameters that we are setting over here should be same, then we can compare the thing with other thing, right? That's the only reason of keeping these values similar, nothing else. So you can check, you will take your value, your cutoff frequencies and sampling frequency, and you can check the results of that, right? So sorry, okay, some error, okay, we may error because the sample cutoff frequency second one is not, so it's 51, then 5500, right? And 1000, right? Then 2000 is my sampling frequency. Press enter. So these are the filter coefficients. Okay, now let's see the frequency response, and this is my frequency response. Okay, so this is all about the black pen window. So let me write uh, for the code for the band pass filter with Kaiser window. Okay, so sir, not band pass, band stop filter, right? We are now dealing with band stop filter with window. Okay, so for that, the input section is same. So what I am going to do here, uh, let me copy the thing, the input part, right? Okay, so let me copy that, paste it here because the input section is same, right? No changes. Yeah, one changes is there where I have to define a variable beta. I am taking beta as 14, right? Then next section is my uh, using built-in function, right? The window designing, the designing of a FIR filter with using built-in function, built-in function, right? So for that we take as a variable that is tabs is equal to FIR win, and then the next parameter is our frequencies, right? Then the next parameter is my pass type option, not pass type, it's pass 0, right? Which is equal to band stop. We are designing band stop filter. So it's band stop. Then the window. This is the most important in Kaiser. Window is equal to, we have to supply two parameters here, that is on it Kaiser. Next one is the beta, right? Okay, so with this we have done with the built-in function. Now generate the Kaiser window. That we are actually going to use in our formula, Kaiser window generation. Okay, so for that wn is equal to Kaiser comma beta, this is equal to 14, right? Here we have to specify the values of beta, right? If you call that, it will not able to call a variable through this window type, right? So I have to specify the beta value direct. Then the next thing is that normalized frequency. I have to print that. Print normalized frequencies of the band stop filter is, I think so, I didn't change this band stop from the initially, like just look at this. Yeah, make changes. Yeah, no worry. Okay, so for that, what is my normalized frequency? Fc1 divided by Fs, right? Small Fs, and Fc2 divided by Fs, right? Then next one is I omega c1, which is equal to bracket Fc1 divided by Fs into pi, right? This is the digital frequency. C2, which is equal to Fc2 divided by Fs into pi. Okay, so we will print this. The digital cutoff frequency of band stop filter is omega c1 comma omega c2, right? Then the formula that we have used is same. So for that reason, what I am going to do here is, let me copy the thing from here and paste it there, because rest of the thing is similar. No any marginal changes we have to do there. So I just copy that and paste it here, right? Okay, I have to make the change that this should be as Kaiser window. Okay, and this also change to change to Kaiser window, right? And no other changes that I have to make. Yeah. Okay, so now let's run the code and see whether we are getting the output or not. So first keep the error of the filter and giving that as 31, and the cutoff frequencies I am giving 500 and 1000, right? Then the next sampling frequency I am giving as 2000. Okay, so the so you can check, these are the frequency components, and this is my frequency response, right? You can see that the refill in the stop band is not there in this window, right? It is we are not able to notice it in the uh, second figure, that is frequency in hertz also, right? If we compare with without window, that is we have done in our lab 8, right? You can check it. This is the my uh, here I actually, in the last part, I generate all the things. So this is, you can see the bend stop or bend reject without window, right? So you can see that this is the frequency in hertz, right? There are some ripple over there, but in case with window, we minimize the ripple in the stop band, right? So I think it is clear to all of you that how to design a band pass and band stop filter with window. Okay, so with this we finished our FIR filter designing. Okay, with and without window we see both types, right? So I think it is uh, clear to all of you. So thank you.